Okay, so suppose we had this equation where a and x and b are all matrices. Now, if we had this equation in algebra 1, and we just had ax equals b, and they were all numbers, we just divide both sides by a, and we would know what x equals. However, for matrices, we only have addition, subtraction, multiplication. We don't have any division. So we can't just divide both sides by matrix A and find x that way. That's a deal breaker. So we've got to talk about the inverse. If A is an n by n matrix, so it's a square, same number of rows and columns, let I sub n be the same size identity matrix. If there exists a matrix A inverse such that A times A inverse equals the identity matrix, and A inverse times A also equals the identity matrix, then A inverse is the inverse of A, and that's how we read that symbol. So this is kind of our version of matrix division. We know addition and subtraction are inverses of each other. We know normally multiplication and division are inverses of each other, but we don't have a division, so this inverse is going to be kind of like our division. So now, if we have the same equation, a times x equals b, if I multiply this equation by the inverse of a, and whatever I do on one side, I have to do on the other side, and since matrix multiplication is dependent on the order, if I multiplied the left side on the left, I have to multiply the right side on the left. Then these two things multiplied together equal the identity matrix. Just so you know, the identity matrix looks like this. 1's on the diagonal, 0's everywhere else. So that's kind of like our version of a 1 in real numbers. So I have x equals the inverse of a times b. So that's how I can solve matrix equations. So for this example, it asks us to find the inverse of this matrix. So we know that if I take a times the inverse, or if I take the inverse times a, that will equal the identity matrix. So if I set it up as the original matrix times some other matrix, we'll call it w, x, y, z, and this is equal to the identity, then I have found the inverse. So I'm multiplying these two matrices together. Try to use some colors for you. So I've got the first row times the first column. So that means 1 times a w plus 4 times y equals 1. And if I keep going, first row times second column equals second entry. So I'll write that over here. 1 times x plus 4 times z equals 0. Now I've got the second row times the first column, negative 1 times w minus 3 times y equals 0. And the second row times the second column, negative 1 times x minus 3 times z, equals 1. Okay, so now I've got two systems that I can solve for w, x, and y, and z. They work out pretty nicely. So I've got y equals 1. Over here I've got z equals 1. So if I go back to these original guys, w plus 4 equals 1, subtract 4, w equals negative 3. Over here, I've got x plus 4 equals 0, minus 4, x equals negative 4. So my inverse, which was this guy, I now know all of those elements. So W is negative 3, Y is 1, X is negative 4, and Z is 1. So this guy is my inverse matrix. So that was kind of a lot of work. So we don't always want to do that much work every time, and especially if A is like a 3 by 3 matrix, we definitely don't want to do that much work. So let's look at this. We've got matrix A, which is elements A, B, C, D, and they're telling us it's invertible, so that means it has an inverse, if and only if A times D minus B times C does not equal 0. And if that's the case and that thing doesn't equal 0, then I've got this nice, kind of complicated but not too bad formula to find the inverse of a 2 by 2 matrix. That thing that we found earlier that had to not equal 0, that's called the determinant, because it determines if there's an inverse or not. So that thing is what we find first in order to find the inverse. So I'll try to show you all that stuff on the same screen. If possible, find the inverse of matrix A. So we're going to do A times D, so that's 5 times 4, minus B times C, so that's negative 1 times 3. So the abbreviation for the determinant is DET, so that's 5 times 4 minus negative 1 times 3. So that's 20 minus negative 3, so the determinant is 23. That does not equal 0, that's a good thing. So that means we can find the inverse. So now, I'm going back to this formula to find that inverse. So the inverse of A equals 1 over the determinant, so 1 over 23, times, and notice I'm switching things around. So A and D switch spots, so that's the 5 and the 4, so I've got a 4, then a 5. B and C stay where they are, but they get multiplied by negative 1, so B becomes a positive 1 instead of a negative 1. C becomes a negative 3 instead of a positive 3. So now I'm just doing scalar multiplication. I'm multiplying each element by 1 over 23. So I've got 4 over 23, 1 over 23, negative 3 over 23, and 5 over 23. And that thing is my inverse.